Okay, so simple DIY engine management. Just as a little bit of housekeeping to start off with, if you're here for any of these engines, you're in the wrong place. I'm actually going to be talking about these, which are engines in a car. For reference, by the way, there's a 45-year-old engine under all the mess there somewhere. Okay, things I'm actually going to talk about today. Engine basics, just so I can get a little bit of a feel for where to go with the talk. Who would say they understand how an engine works? Okay, cool. Who would say that they are comfortable with how fuel injection works? Okay. And who would understand what I meant if I said the term volumetric efficiency? Right, cool, that's fine. I'm going to be talking about the functions of an ECU or an EMS. So ECU typically being electronic control unit or engine control unit, or EMS, engine management system. The two terms are somewhat interchangeable, with EMS being the slightly preferred terminology for what I'm talking about today. I'm going to talk about the various sensors involved with an EMS and what I/O they perform. I'm going to talk about why Arduino is the best possible platform for a hacker EMS. I'm going to talk about why Arduino is the worst possible platform for any EMS. I'm going to talk about how to bring it all together on the cheap, so make it really accessible. And I'm going to do a bit of a demo and questions if the demo gods allow it. Apologies in advance if there's anybody out there listening from other EMS projects. That this is a bit of an aberration compared to what other people are working on sometimes. Okay, engines need managing. Yes, like us all, engines do need managing. The basics of a four-stroke engine are essentially that we need to get some fuel in, and we need to determine how much that fuel is, and we need to ignite that fuel at the correct time. It is mostly a math problem, so I chose a really good CPU for math. Determining the fuel requirements that we have based on the load and the speed of an engine, implementing the calculations required for it, and taking into account a bunch of edge cases, for example, starting an engine in the cold, acceleration, outside temperature. Oops, sorry, let me jump back. Ignition and spark management. So this is the timing of a spark plug. This is actually more difficult than fuel management in a lot of ways. It's a very precise timing issue. And also running all the extra bits. So all the things that an engine needs to run, controlling a fan, controlling the idle, and protecting the engine in case of any component failures. So anyone who's ever worked with engines will probably seen a diagram like this. This is essentially running through the four cycles or four strokes of an engine. We take fuel in, the fuel is compressed, it's then ignited, and then we have an exhaust stroke to get the gases out of there again. There's two things going on here that you can see. There's a fuel injector on the left and there's a spark plug in the centre. At various stages of the cycle you can see both of those going off. It's the control of those which I'm going to be talking about today, and that's what we want to handle with an engine management system. All right, so why would you want to do this in the first place? It seems like it should be a solved problem. Well, back in the old days, we didn't have fuel injection, we had carburetors. They were, at best, an estimate to try and get fuel into an engine, and we had distributors, which controlled the timing of an engine. They did it okay, but they had a lot of limitations, particularly being mechanical. A fully programmable engine management system gives you total access to the fueling and timing of an engine. If it's set up correctly, you can have as much or as little fuel as you want, and you can make the spark go off whenever you want in that cycle. It's used primarily in race engines. An awful lot of race applications can benefit from this. And it's very common with engine swaps and conversions and things like that as well. The existing options out there for aftermarket engine management all cater to different audiences, none of which were what I really wanted to target. They were either too closed. Now the aftermarket engine or the aftermarket automotive industry is ridiculously closed and secretive. They're like a lot of IT vendors in that way, I suppose. But they don't like giving anything back, and they certainly don't like telling you how their products work. Some engine management systems, for example, are as limited as you can't set your own tune. You have to send it away. They put it on and they will send it back. Really not what you want. Too expensive. These systems can be easily up to $4,000, $5,000. There are lower priced systems with varying capabilities, but there were none as low as the area that I wanted to hit. Too complex or too simple. So when I'm talking about complexity there, I'm not talking about complexity to use, although that is another issue. I'm talking about complexity to actually hack on. So if you just want to play with engine management and go and get an engine running, that's fine. There are a lot of options for you. If you want to actually know how the system is working, it's a very, very steep learning curve in the few areas that will actually even let you do that in the beginning. And some are too simple. Some are just, turn the knob to make more fuel go in, turn it the other way to make less fuel go in. So we needed something that was going to be very hacker friendly, very simple, and something that people could actually learn a bit on. There's quite an overlap of interests in this area. A lot of car people are interested in electronics. A lot of electronics people are interested in cars. Sometimes they don't always know how to best work with each other. So this was a good project for trying to help people understand how the two can relate in what is really the heart of an engine control system. Learning as well was a big one. There's a really massive model engine market out there for building small-scale engines and running them. Those guys are desperate for fuel injection gear that they don't have to spend thousands on. So that was another reason why we're doing this. Projects like Formula SAE are all using closed systems at the moment as well. And, who wouldn't want a fuel-injected go-kart or a lawnmower for that fact? Virtually every person who's ever made an engine management system has a fuel-injected lawnmower. It just seems the way to go. All right, so the goal was a hacker-friendly and advanced engine management. I didn't want it to be too simplistic, with as low a barrier to entry as possible for under $100. I'm using Arduino. It's simple, it's cheap. Yes, it's limited in capabilities, but it does have what we need. All the code in this is compiled straight up through the Arduino IDE. You can have it running on an Arduino within 30 seconds of plugging it in. It will all just compile and work. There is no assembly knowledge required. There are very, very small amounts of assembly in the code, but they are sort of black box and you don't really need to know what they're doing. Sorry, you need to know what they're doing. You don't need to know how they're doing it. It will require a little bit of background engine knowledge. If you can install an engine management system, you could easily install this. But if you wanted to hack on it, this is going to be a lot simpler than other options. But what it definitely isn't was just going to be a testbed device for something that sits on the bench. I really wanted something that was capable of running a car properly. All right, so how do we go about doing this? Obviously, you're going to need some inputs to control an engine. The absolute must-haves that you need are the engine speed. You need to know how fast you're going. In this case, that translates to RPM. Engine position. Now, this is relative to a thing called top dead centre. Back on the diagram that we looked at before, which is this one, you'll note that the engine's actually going through 2 revolutions in its 4 cycles. Top dead centre occurs when the spark plug goes off, essentially. There's a little bit of timing there, but it's basically there. Everything is relative, therefore, to that point. Engine load, so this is basically a measure of how hard the engine's having to work, and I'll talk about that a little bit more later. And a few constants, so you need to know the engine size, the injector size, and what flow rates they're going through and that sort of thing. So those are the absolute must-haves. What you really should have to run an engine as well is the engine temperature, so you need to know whether it's ice cold or whether you're nicely warmed up. You need to know the air temperature of the surrounding air. As most of you would probably know, the temperature of the air will affect how dense it is, which affects how much fuel you're going to need to put in there as well. And an O2 reading. This is done by a wideband or a narrowband oxygen sensor, which is fairly common along all cars these days. Wideband becoming much, much more common. Now, widebands are an incredible piece of gear. If you ever look into how they work, it's simply phenomenal. But they essentially give a reading of how much unburnt fuel is left after it's gone through the 4 strokes.
So just a question.
Yes.
Your system at the end, would that be closed loop?
Yes. Yep. Not in the demo, but yes.
Sorry, don't mind just rephrasing questions so we can get to the...
Oh, sorry. The question was, is this system closed loop using O2? And the answer is yes. All right. So this is an example of what's called a crank angle sensor. It's one kind of implementation of it called a missing tooth sensor. The sensor here can be any number of things. It can be a Hall effect sensor, which is nice and simple. It can be a variable reluctance sensor, or it can be an optical sensor. What's essentially going on is this cog here, or this wheel, will spin around at crank speed. This gives you 2 pieces of information. Firstly, every time you detect a tooth, you can tell how fast the engine is going and calculate RPM from that. You'll also note, however, that there is a missing tooth here. Now, the missing tooth is very important in that that also gives position information for the engine. You can detect when you've missed that tooth and then know where you are in the engine cycle. These wheels come in a number of different styles. You can have 4 teeth. They're typically known as a 4-1 or a 12-1 type of sensor. They range anywhere from 4 teeth -1 up to about 60 teeth -2. Obviously, the more teeth you have, the more accurately you can know where the engine is in its cycle. A 36 -1 tooth wheel, for example, will give you 10 degrees of fixed accuracy. Between those teeth, you're going to be estimating where you are in the cycle, or how far you are from the next tooth. A wheel like that is a 36 -1 wheel. Very, very common, for example, on Ford engines. They've been using them for a long time. Very, very simple, very, very hacker friendly once you have access to the sensor. This is sort of how they're set up. Once you set the engine to top dead centre, you'll be pointing at a certain tooth. If you rotate the engine so that the first tooth after the gap is now pointing at the sensor, you take a reading for what angle you're at, and you can know where the engine is after that. So, logging a sensor like that gives you a pulse train that looks roughly like this. The y-axis here is a measurement of how long it took between each teeth, as measured in milliseconds. In this case, it's a 36 -1 wheel. The pulses between each tooth are about 0.7 of a millisecond there. The long ones that you see are approximately twice the height of the regular ones, so you know that you've missed a tooth at that point, and you know where you are. Does anyone want to guess at what's happening in that picture? Sorry? Changing revs, yes, but it's happening in a very specific way. This is actually what it looks like when an engine is cranking. And every time these go up, you're hitting a compression stroke, which makes the starter motor slow down. You've got to be really careful, obviously, not to put your missing tooth, right in the middle of there, because it becomes very hard to detect at that point. So in the 4 strokes, one of the strokes is compression, where the engine is compressing the mixture that you've got in there. Now, when you're cranking an engine on the starter motor will be applying a fixed amount of force. So when it gets to that compression stroke, it has to work harder and it will slow down. So that's why you get this kind of waveform. Okay, so load methods. This is essentially a way of determining the amount of air that's entering an engine. There's a number of ways that you can do it and that manufacturers have done it in the past. There's a mass airflow sensor, a throttle position switch, and manifold absolute pressure are the most common methods. I'll talk about each of those in just a minute. MAF was traditionally used very early on in electronic control systems. It went through a bit of a heyday, faded out a little bit because it had a lot of weaknesses, starting to come back now as newer systems are much better than the old ones. MAP, manifold absolute pressure, simply works by measuring the vacuum that appears in the engine's intake. The harder an engine is working, the more closed the throttle will be, for example, the more perfect a vacuum will be. In an ideal world, an engine would be able to bring in the same amount of mixture as its capacity. So if you have a 400cc cylinder, it would be able to suck in 400 cc's of air and fuel. In the real world, that won't happen. So you have a loss, essentially, which is what we refer to as volumetric efficiency.
That's, of course, assuming you're not using turbocharging.
Correct, yes. Turbocharging will increase your volumetric efficiency above 100%. Yep. There's an example of each one of the sensors. The MAF sensor on the top left, otherwise known as a hot wire sensor. So it'll heat one of the wires that you can see going across there up to a known value, and the amount of air passing over those will cool those at a fixed rate. You can see in the picture on the top right, this is a throttle position switch. If you see the little knob sticking out at the end, you would just hook up essentially a variable resistor to that. As it turned, you'll get to see how open or closed it is, and from that you can make an estimate about how hard the engine's having to work and how much air it's getting in. Down the bottom you have a manifold pressure sensor, fairly simple. It will measure, obviously, absolute pressure between a given range. Interesting to note that only 2 of these methods actually measure air, being the MAF and the MAP sensor. The TPS sensor, throttle position sensor, will simply try to guess how much air is passing through based on how hard you are pressing the throttle. All right. Required outputs. So what are we actually trying to achieve? Fuel injectors, obviously. This is the main thing that we're trying to fire. From an electronics point of view, they behave pretty much like any other solenoid. They'll have the normal kickback that you need to adjust for. They work basically by applying about 42 pounds of fuel pressure to one side of a solenoid, top end here. When the solenoid opens, it will spray out the other end in a given pattern. What you do need to take into account for, though, is the open and close times for the injector. And they will be, so each injector will be rated at a given pressure, so you know if it's open for 1 minute, it will have sprayed this much fuel. Okay, coil control. This is determining when the spark will occur within an engine. You have a coil that's charged for a given period of time. It's approximately 4 milliseconds that you need to charge one of these coils for. When you stop charging it, it will discharge and you'll get a spark on your spark plug. This is known as dwell time, for anyone who knows the reference. Traditionally, these have been very high current, high voltage devices and required fairly specialised drivers. These are now largely replaced in engines by what's referred to as a smart coil or a coil on plug. It looks something like that, and there's one over here somewhere, and a very basic diagram of how they work there. But the upshot of it is that you can drive it from a 5-volt logic level off a controller, which is really handy. They will also take into account things like overdwell, so if you charge the coil too long, it will discharge by itself. And there's a few other bits and pieces that it's nice for an ECU to be able to control as well. So idle control, when an engine is cold, it's going to have different conditions that need to be met. Fan control, cooling an engine, boost control, so on and so forth. There's any number of things that an ECU is well positioned to control. All right, so the math that's involved here. Volumetric efficiency is a very, very important one. It is simply a measure of how efficiently the engine is able to pump air. An engine is nothing more or less really than a big air pump. The more efficiently you can get air in and out of an engine, the more effectively it will run. Typical naturally aspirated, so non-turbocharged engines will run at around 80% volumetric efficiency when they're at standard operating RPMs. So that means that if it's a 400cc cylinder, it'll be taking in about 80% of that volume in every cycle. We obviously need to take this into account when deciding how much fuel to use. Yep.
Does that mean that 20% of the previous exhaust that stays in the cylinder as you're putting the new fuel in makes it the next go?
It can mean that it won't be all exhaust, but... Oh, sorry, the question was, does that mean that the 20% of the exhaust from the previous cycle will still be in the cylinder. Certainly some of the exhaust will still be in there, yes, but it really means that you're not able to, you're still going to be operating under a partial vacuum, is the answer. Yep.
So it's more like you've only got 360 cc's and the 400 cc's.
Correct. You're effectively making the cylinder smaller. Yep. The fuel algorithm that is used, and this is used across virtually all ECUs, you have a fixed constant, which is typically referred to as rec fuel, and it is a measure of how much fuel would be required at 100% volumetric efficiency. So we assume that the engine, or the cylinder, sorry, is able to suck in its full capacity, and that's what we call required fuel. It's made up of a number of things, such as the engine capacity and the injector size and that sort of thing. We then multiply that down, or up, in the case of turbocharging, based on a VE map lookup, and I'll show you a map in a minute. And then we make a number of adjustments, or percentage adjustments, to the final figure based on acceleration. If you slam your foot down very quickly, the engine will require a short burst of fuel, otherwise it will stutter. Any air temperature correction that needs to occur, any engine temperature correction that needs to happen on a cold start, or if you're in the snow, for example, and any barometric correction that we need to take into account depending on your altitude. And to all that, we add a thing called dead time amount. Dead time is the amount of time it takes to open a fuel injector minus the amount of time it takes to close a fuel injector. So during those periods of time, they will be spraying a reduced amount of fuel, and you need to take that into account as well. So in the end, you get an injector pulse width, which is dead time plus your required fuel constant times a VE lookup. Now that'll be RPM and either TPS or MAP, depending on what load method you're using, times the sum of corrections, or possibly product of corrections is probably more accurate there. Any questions? That's moderately complicated.
The dead time is variable based on battery voltage as well?
Variable based on battery voltage as well, yes, and also the specific to the injector as well. So look, battery voltage doesn't affect it that much. That's the one time it does affect it. Sorry, the question was how much does battery voltage affect dead time? You can live without it if you need to. It's
The variance for the dead time over 8 to 40 volts is about 10%, so it's not a huge amount.
and typical dead time is about 1.5 milliseconds.
The current Bosch injectors are about 700 microseconds.
Yeah, the newer ones are becoming very impressive. Yes.
Are you only using TPS or MAP, or are you using TPS to correct for MAP in some cases?
So the question is whether I'm only using MAP or TPS, or whether I'm using one to correct the other. I'm using one or other for the standard lookup, but typically using a blended mode for acceleration enrichment. The reason we do that is because MAP sensors are a little bit slow, and when you shove your foot into it, they can take 250 milliseconds to react properly, whereas a TPS will be virtually instantaneous. So we blend the two at that point. There's potentially many other adjustments that you need to take into account as well. Things like rev limiters, run lean protection, so in case something's gone wrong and you want to cut spark out, overboost protection, traction control, launch control. There's many other things that an ECU can do to vary those numbers, but those are the typical ones for a normal case. That's an example of a fuel map. It's what we refer to as an 8x8 map. Two representations of it is just a table view and a graph view. This is a 3D map, so you get obviously 3 dimensions. One thing that is very important to do, particularly when you're running limited map size, which is this is 8x8. Some ECUs now are running 16x16 or 32x32. In this case, I'm limiting it due to the Arduino's processing speed, but I think there is potential to move up. Is a thing called running interpolation, which is where if you are between, for example, 3,000 and 4,000 RPM and between, let's say, 50 and 60 TPS, you're not just going to be picking one of those values out, you're going to be doing a 4-way average of the figures that you're falling in between. So that's really important, and it means you can get away with much smaller tables than you'd otherwise need, because you only ever have to tune the non-linear portion of the table. Anything that's linear, you can just rely on interpolation for. The maps like these are all stored in EEPROM, loaded upon startup from the ECU. They're stored there along with any calibration data and that sort of thing as well. Any questions so far? Nope. Excellent.
What are the actual limitations? Because like my cars are running fuel maps that are usually 32 by 16, or it just depends on the load points
Yep.
that are needed to tune it. So it's relatively dynamic based on the behaviour of the fueling drivers and so on. So what are the actual limits that you're finding that the Arduino can handle?
I haven't, sorry, the question is around the limits of the Arduino's processing, if that's correct. I haven't hit them yet. I've started off simple and we'll get things more and more complicated as we go along. I'll talk a little bit about performance in a minute, but yeah, short answer is I haven't hit them yet, so I can keep adding things until I do. All right, enough theory. How's this actually implemented? The bits involved. It's a very difficult thing to try and treat, or to try and be able to work with every piece of automotive hardware out there. There's vast differences between manufacturers and models and that sort of thing. So what I've aimed to do is pick a specific set of automotive hardware, which greatly simplifies the target platform. I'm using an Arduino Mega 2560. Any 2560 variants of that will probably work. The other ones that will potentially work are any 1280 or 640 AVR chips. The reason for this is because these are the only ones that have sufficient 16-bit timers. I'll talk about this a little bit more in a minute again, but it's without those timers that the Arduino simply wouldn't be powerful enough to be performing this function. At this point, I'm running a fairly basic I/O shield for the Arduino. It consists of 4 injection driver circuits, 4 ignition control channels, and some relevant protection for some of the inputs, which is simply done via an optocoupler. The really nice thing about an Arduino compared to other environments as well is that it runs at 5 volt. Pretty much every automotive sensor out there runs at 5 volts, so it makes life a little bit simpler in that regard. Okay. That's a look at the board. It's pretty simple. You can see the MOSFETs here are the injector drivers. There's a couple of channels there for the ignition, and the opto over there for the inputs. There's also inputs there for all your coolant, intake air temperature, TPS, all those sorts of things. This is a very early design board. I'm working on a second board at the moment, which is going to have a map sensor and relays and stuff built in to make life a little bit simpler. That's a really good question. I've only tested it with, the question was, does it drive high or low impedance injectors, which are 2 types of injectors you can get. At the moment, I've only tested it with high impedance injectors. Theoretically, though, the drivers are capable of running low impedance injectors as well. I just haven't tested. That's a really basic schematic. I think that was just 2 channels of it rather than the 4. We won't look at it too much now, but if anyone wants it, it's there for the future. So the really big problems that you face. A lot of people, when I asked around the ECU community, said, you can't do it with an Arduino. Everybody rolls their eyes when you mention it. Possibly they said it shouldn't be done rather than it couldn't be done, because you hit a lot of problems that you really shouldn't. The obvious stuff is floats. You can't use floats, obviously, on an Arduino. It's unfortunate because you need them a lot in an ECU, so you have to find workarounds for that. To keep things simple, everywhere I've needed a float, I've written a float implementation of the code, commented out and written a non-float version below, because the non-float versions of the code tend to be a little bit hard to read, a little bit hacky, but the float versions are fairly simple to read. So it's a nice mix there to be able to see what the code's actually doing, even if you can't understand the individual lines. Who's ever done any benchmarking with division operations on an Arduino? They're basically as slow as floats. They're horrible, really, really bad. So the one area where I have got into a little bit of assembler is replacing the division operation. It's unfortunate that you have to do that, but Without it, you simply wouldn't get the performance that you need. And there's a lot of limitations in the Arduino software, which is unfortunate as well. You can't set an O level through the IDE. If you compile this at O3 rather than the default, which I think is O2, the performance is so much better than what you'd ordinarily get, but it's not really something someone playing around with it can easily do. So I've limited, I'm not using that at the moment. Obviously, there's really slow I/O code from the Arduino. The board itself is capable of a lot better I/O. Things like messing with the ADC clock speed can make a big difference. I'm using Gus's fast digital I/O library, which is pretty awesome. That's made a big difference. The end result is that the main loop, which does all the calculation and everything, runs at about 1,300 loops per second. The general guidance when making an ECU is that you need to be above 500 loops per second. So I've got a bit of overhead in there at the moment. Using the scheduler system, the timing accuracy I've got now is well below 100 microseconds. You can get away with anywhere up to maybe 250 microseconds. And that's at 10,000 RPM, so it should be heaps. The timing accuracy is much more important for the ignition code rather than fuel injection. As long as you've got the right amount of, roughly the right amount of fuel, an engine will run, and it will actually run quite well. But timing, if you get that out by a couple of hundred microseconds, it's not going to run well at all. All right, so how do you actually make all this work? You need to abuse the timers that the Arduino has, really. The only thing that makes this work, are the timers that you have available on the 2560. There's 4 general purpose 16-bit timers. There's 2 8-bit timers as well, but they're pretty much useless for what we want. They simply don't have the resolution. One of the timers is used by Arduino, and I've left that alone. So I've got 3 available. Each of those timers has 3 compare channels, which leaves you, if you're using 1 per injector and 1 per ignition cycle, if you've got 4 channels, that leaves you 1 left over. Yes?
Just for those not familiar with the Arduino, or even what is a timer?
Sorry, a timer is something that you can say, okay, when you've had this many ticks, perform an interrupt on the CPU, and then you can run a separate piece of code outside the main loop. Obviously, you're going to be limited to how much processing you do outside the main loop, so you need to be careful with that. But they are very handy for this type of timing work. Yeah, okay. Pre-scaling the timers, by the way, to 256 give you a theoretical accuracy of about 16 microseconds, which is more than enough. Okay, so how do we actually do it? Each schedule, now you can have an injector schedule or ignition schedule. In this case of this board, there's 4 each. That's enough, by the way, for anyone who's interested in engines to run 4-cylinder sequential or batch mode up to 8 cylinders, probably beyond 8 cylinders as well if you don't want to do ignition. So schedules are all run as interrupts to the main loop, obviously. The main loop will sit there and calculate the pulse width and the dwell time and the dwell schedule just as fast as it can. It'll sit there processing those. It'll set schedules to run at the points in time that it calculates and then go back to calculating the next lot. When a schedule gets called, it'll go away, it'll turn on either an injector or a coil to start charging and record a duration. After that duration, it'll again exit the main loop and turn either the injector or the coil off again. The aim is to spend as little time as possible in the main loop. Outside the main loop, and as much time as you can in the main loop. The main loop will simply keep running, and it might set a given schedule for a certain injector 20 times before it gets run. The idea that every time it runs, it's going to be giving a more accurate value than it otherwise would have had. This is where this code base differs a lot from other ECUs. Other ECUs have the raw CPU power to not need to do things this way, and they'll typically only use a single interrupt that runs every, 100 microseconds or something like that, and then does all the calculations within the interrupt. We simply can't do that with an Arduino. It doesn't have the processing power, so we need to rely on those schedules and those timers as much as we can. As I said, you can call a schedule any number of times, but when it reaches its scheduled deadline, it'll start firing, it'll start running, and won't accept any more modifications until it finishes. Okay, how are we doing for time? Okay, cool. All right, any questions before I move on to a demo? Yep.
So you've got all sorts of sensors around the place.
Yep.
Obviously you want to keep the main loop as tight as possible.
Correct.
But going out to pull one of those sensors might take a while. How do you manage that?
Yep, so the question is how long it takes to read sensors. It is a problem. Doing things like I mentioned, changing the ADC clock speed for any analog reads makes a huge difference without too much impact on resolution. The Arduino, as in its default configuration, runs the ADC much lower than is spec'd for the AVR chip, so you can wind it up a fair way before it runs out of spec. And things like that make a really big difference to the loop count that you get for the main loop. Yes? Yep.
When you're saying that if problem because you need floats, it's probably going to be dumb, but I'm just wondering why you can't just multiply everything by whatever precision you need.
Sorry, I missed the start of the question there.
Why you can't just use fixed precision and multiply everything by precision that you need? And
You can, and that's essentially what I'm doing, but it gets a little bit complex because you've got a lot of things needing to go into some of these calculations. That is the answer. That's how you do it. And the question, sorry, was around why you wouldn't just use fixed accuracy instead of your floating calculations. It's sort of hard without showing you the code, why it becomes messy. It's simple enough to do, it's simple enough to explain. When you look at the code, it's a bit of a mess, simply because of how it has to fall out. Yep.
Dual spark, big little injectors, like rotaries kind of things.
Rotaries support, no, not yet. Theoretically, not too hard. Dual spark. Dual spark, again, requires an extra map because you need to, assuming you don't have a fixed amount of time between the two sparks. If you just want a fixed amount of time between dual sparks, it's really easy to implement. If you want a variable amount of time, you need another map. And I'm starting to run out of memory a little bit. It can be done. Yep. What was the third one, sorry?
Big little injector. So
Big little injectors.
smaller, big
Switching or concurrent running?
staging kind of.
Probably not that hard to implement. Yeah.
Rotaries run a primary and secondary injector setup.
Do they run at the same time, or does it switch from one to the other?
If you look at the way the standard ECU works on one of these things, it switches at a low point of about 3,500 RPM from running just the primaries to running both the primaries and secondaries.
That's pretty easy to implement then.
Yeah, I've got a custom setup for one of the ECU on mine, and it switches in what they call common mode. So it goes
Yep.
from running the primary injector into the one down duty cycle, and then switches to running all four injectors in one go.
Yep.
We tend to back off the primary a little bit whenever they start up secondary in order to not have the start 12 secondaries.
That's in terms of the ECU. There's certain
Yeah, I think we might just keep moving on for the sake of time. Happy to talk about it afterwards. All right, how are we doing for time? Have we got any time?
Yeah, I've got about 2.5 minutes.
2.5 minutes. Okay. If we only got 2.5 minutes, I'm probably not going to set this up because I didn't quite get to do it before we started up. I'm happy to do it over the lunch break though, if anybody wants to look. I do have some videos instead, in case we did run out of time.
kind of fail safety
Yep.
and whether it's just going to make things explode.
Sure, it might.
If you get the timing wrong, it will
If you get the timing wrong, it can be a big problem. A lot of this is left up to the user and what numbers you put into your fuel maps. The difference at high RPM between a 5 millisecond fuel pulse and a 20 millisecond fuel pulse is the difference between a well-running engine and something with a hole in a piston. So you've really got to get it right, and a lot of that is left up to the user. The ECU itself will implement that, no worries. There is a run lean protection that I've put in, where if it notices that you're running really lean, it'll just cut the spark out, so your engine will just stop effectively until it gets back to a satisfactory condition. Other than that, it's really up to you to make sure your fuel maps aren't stupid, and your spark maps as well, for that matter. Yep.
Any automated testing or?
Yes.
for
Things like
stopping
okay.
and throwing you in?
Automated. For that, no. Not yet, no. I've manually tried to test as many edge cases as possible, but no, I don't have anything automated yet. It's a good point. As far as other testing tools, for example, I've got a little Freetronics Leo stick there, which is acting as a pulse generator, so you can set RPM and everything based on the Leo stick. Yep.
So, a couple of questions. First, a comment on testing.
Yes.
You can use SIM API.
Sorry?
You can use SIM API to emulate your microcontrollers on the PC, so just to make sure that inputs and outputs are in the correct ranges before you actually go on to testing.
Yes, that I have used in the initial stages. I think the more worrying thing is if you get into bizarre edge case scenarios that could blow up an engine.
So the actual question though is O2 sensors.
Yes.
Do you have capability of reading those and altering the
Yes, so the question there is whether I have capability of using O2. The answer is yes. I'm not even going to bother with narrowband O2. There's a lot of myths around narrowband O2, but they're junk. They can only tell you whether really you're running lean or rich. They can't tell you at all, really, how rich or how lean you're running. So that they're a bit useless, I think. Wideband O2s, though, certainly. And I am using those in a basic closed loop mode. This, incidentally, though, through the software I'm using, will actually do an auto-tune function. The tuning package I'm using is one that already existed. It's called Tuner Studio. And it will do automated tuning of your fuel maps based on a wideband O2, and it works on this. So.
All right, we've probably just got time for one more question, just up the back there, that's all right.
Can you connect a NOx sensor to automatically delay the engine starting with this thing?
Yeah, you can. NOx sensors are difficult in that a NOx sensor is tuned for a given block. There are starting to be programmable NOx sensors coming out. They're a little bit experimental and they're very expensive at the moment. Look, some NOx sensors you can move from one engine to another and you're going to be fine, but trying to make a generic NOx sensor implementation is really difficult. They're unfortunately very specific to each engine at the moment. It can be done, sure, but I'm not doing it yet.
Links to all your software? Links?
Right there.
And that references the Tuner Studio software that you mentioned?
It doesn't actually, but Tuner Studio is pretty easy to get. Sorry, I just should have put a link up for that. But if you Google Tuner Studio, you'll find it like that.
Did you still want to run a demo when we go into lunch?
I'll probably run a demo during lunch if anybody's interested in it.
Break up.